Hello and welcome. What did the vacuum cleaner say to the mop? I don't know about you, but I'm tired of being pushed around. In this video, we're going to continue our work from Packet 22, trying to solve the area problem. And solve it, we will. But first, let's review some handy notation for writing summations. This notation is called sigma notation, also called summation notation. Here are some examples. If we want to write the sum 1 squared plus 2 squared plus 3 squared all the way up to 6 squared, we can write it using this capital sigma. This is a capital sigma that represents the sum, and here we're taking the sum as I goes from 1 to 6. This is I is representing, it's called an index, and this is just a variable that's going 1, 2, 3, 4, 5, 6, and you're plugging in these I values into this I squared to get each term. Now the capital sigma means you're going to be adding those terms up. So let me do a little bit of terminology. This is the first term. This is the second term. And so on. So each of those things that are separated by the pluses are the terms. And then the I is the index in this example. So I is the thing that creates each term. The variable I is running from 1 to 6, and it's creating each of those terms. And the way you create it is you plug it into this formula that's to the right of the capital sigma. So I equals 1, you plug it in, and you get 1 squared. I equals 2, you plug it in, you get 2 squared. And we're going to add those two things together because we're talking about the sigma notation, which stands for a summation. Now the last I value you're going to plug in is at the top. This is I equals 6. Now most of the time you don't really write in the I equals because you already wrote the index starts at 1, and so this 6 on the top is also talking about I. So it's usually a little redundant to write I equals, but it's probably worth it to mention that because sometimes people get confused about this 6 meaning the number of terms, but it only means it only coincides with the number of terms if the index starts at 1. But if the index started at 0, then it's not going to coincide with the number of terms. There you'd have, if I started at 0, then you would have I equals 0, I equals 1, I equals 2, I equals 3, I equals 4, I equals 5, and I equals 6, which would mean 7 terms. So this is all to say that the 6 on the top is an I. It's an I value. It's the last I value. On the next example, we have f of 1 plus f of 2 all the way up to f of 100. You can write this compactly as the sum as I goes from 1 to 100 of f of I. So each of the terms looks like f of I, where I runs from 1 to 100. In programming, this would be like a for loop, where you're just adding up every single term that's generated by the for loop. Next example, we're going the opposite direction. We're taking something that's in summation notation or sigma notation and expanding it out. So here we would take I equals 1, plug it in, and you get a sub 1 for the first term. Then put a plus, then plug in I equals 2. So that would be a sub 2. Then put a plus, then you plug in I equals 3. That gives you a sub 3. All the way to the last I value, which is n. So plug in I equals n, and you get a sub n. Now the term that comes right before that would be n minus 1, and so that would give you a sub n minus 1 as an example. Next example, we're also expanding, so you can write this as you can plug in the first I value to get the first term, then put a plus, then you plug in I equals 2 to get the second term, then put a plus, then plug in I equals 3 to get the last term. And then you can evaluate all of these, and you get 1 plus 1 plus 1, which is 3. Now, one of the things is that you can rearrange the terms, so that allows you to distribute the sigma across pluses and minuses. This example shows why that can happen. So let's say you have the sum as I goes from 1 to 3 of I plus I squared. So here you would plug in 1 to get the first term, then you put a plus, then put in a 2 for the second term, then put a plus, then 3 for the third term, and that's your last term. Now we can drop all these parentheses because there's nothing to distribute in here. And we can move all of the first terms up to the front. So the 1, the 2, and the 3. The terms that were coming from I, we can move up to the front. And then the terms that were coming from the I squared, we can move to the back. Then we can write the sum of the first 3 terms as the sum as I goes from 1 to 3 of just I. After all, those 1, 2, 3 terms were generated from the I. And then the next 3 terms, the 1 squared, 2 squared, and 3 squared, those ones we can write as the sum as I goes from 1 to 3 of I squared. So through this work, you can see that the sigma notation can distribute across pluses in this way. So in general, the sigma notation distributes across pluses and minuses as well. Also, you can take a constant. If all of the terms of the summation have a constant multiple in front, so they all have the same coefficient, then you can pull that constant or that coefficient out of the entire summation. This is essentially just factoring it out of every single term. So then you would get that constant times the sum of what's left from all the terms. So as an example, the sum as I goes from 1 to 10 of 2 times the square root of I, you can rewrite as 2 times the sum as I goes from 1 to 10 of the square root of I. You can factor out that 2. Kind of like how the constant coefficients can be pulled out of limits, they can be pulled out of derivatives, they can be pulled out of antiderivatives or integrals. And here, summations as well. The last note here is that if you add up a constant n times, then that's going to just give you n times that constant. So here the idea is you've got c plus c plus, sounds like c plus plus, c plus c plus, and then all the way to the last c, which is the nth c, and you have n of these. But that repeated addition is just the same thing as multiplication. You can just, instead of doing c plus c plus c plus c n times, you can just do n times c, and that gives you the result. So if you have the sum as I goes from 1 to 99 of 2, that's like adding up 99 2's, which is the same thing as 99 times 2, which gives you 198. Now some kinds of closed forms of these summations are going to come in handy. For example, the sum of the first n numbers, so the numbers 1 through n, you can calculate with this closed form, n times n plus 1 over 2. This is something in pre-calculus that you show, but we're not going to spend the time in this particular video to do that. If you're interested, always feel free to contact me to ask. It's fun to go over that one. Now the second one is the sum as I goes from 1 to n of I squared. This is the sum of the first n squares. So this would be like 1 squared plus 2 squared plus all the way up to n squared. So it turns out that that is equal to n times n plus 1 times 2n plus 1 all over 6. That's a closed form of this summation. Closed because it has a finite number of calculations here, whereas here, well, it's a finite number of calculations, but that expands as n expands, whereas here it's the same number of calculations no matter what n is. So perhaps I misspoke when I said finite number of operations. They're both finite, just when n changes, this closed form doesn't change the number of calculations that you do, whereas here every time n increases, you're doing one more set of calculations. There's another one for the sum of the I cubes. So this is 1 cubed plus 2 cubed plus 3 cubed and so on. And it turns out that a closed form is n times n plus 1 over 2, all raised to the power of 2. Which is kind of interesting because if you look at the sum of the i's, you get n times n plus 1 over 2. The sum of the I cubes is that squared. So there's once you know one of them, you know the other one. Now the middle one is a little bit trickier to remember because you have that extra 2n plus 1 over 6. But if you can just remember there's that extra factor, it's kind of like the top of the sum of the i's, but you have that extra factor there, and there's a 6 on the bottom instead of a 2, then you've got the sum of the I squared remembered. So if you can remember it, then you can remember it, is what I'm saying. I'm afraid I don't have a lot of good mnemonics for that one. Well, let's look at example 1. We have the sum as I goes from 1 to 15 of I cubed. rather than writing out 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way to 15 cubed, let's use our nice closed formula, n times n plus 1 over 2 quantity squared. So here the n would be 15. This is like our n right here. That would be 15. That didn't really show up too well. One of these days maybe I'll practice before doing these. Okay, so we're plugging in n equals 15 to the I cubed formula. And when we do that, we get, well, 15 times 16 divided by 2, which is 15 times 8, which is 120 squared, which gives you 14,400. Much faster than 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way to 15 cubed. Now the second example doesn't really have an I by itself, right? It would have to be its own term for us to do that summation. We can't just do the summation of I and then the summation of I in here. The summation doesn't work its way into products of things. It only can distribute across addition and subtraction, like we were saying in the previous page. What we could do, though, to break it up by addition or subtraction is distribute the I here so that we have two separate terms. We'll have 2i squared and then I. Distribute that I. Now what we could do is use those properties to say that the sigma, or the summation sign, is going to distribute across the addition. So we'll get the sum of 2i squared plus the sum of I. And then use that other property that says you can take a constant out. That was like the second property we looked at. You can take that constant of 2 out. And you're left with I squared inside that first sigma. Now that we've worked in the sigma into the I squared and the I, we can use these I squared and I formulas to help us figure out what the rest of the answer is here. So for the I squared, it's going to be n, here the n is 10, times n plus 1 times 2n plus 1 all over 6. And then for the i's, you've got n times n plus 1 over 2. The i's have it. And if you work these out, you get 2 times, this will be 385 inside of those brackets. And here you'll get 55. So you end up with 825. These shortcuts for finding the sum of I, the sum of I squared, the sum of I cubed are going to really help us out in the next example. Thanks for watching this video, and see you in the next one.